Okay, great. Everyone can hear me, yeah? Uh,
Yeah.
okay, thanks. Okay, so let's start. All right. So previously, at least for H8, okay, we actually talked about potential difference, okay, and then, I think for those who are here, let's just do a quick recap. Okay, so basically potential difference and the idea of EMF. EMF is more like the energy taken in by the charge through the battery. Okay, so as we calculate EMF, we calculate the potential difference between uh say E and A, right? So VEA will probably be our EMF, okay? And the difference between VAE and EA is that is the path taken, right? So for AE is taking this path, whereas for EA is taking the pink path, right? And you realize the difference. Um, and even though they may be the same in terms of magnitude, in physics term, right, they actually mean different thing, okay? Because from EA is energy gained by the charge, okay? So this one is a gain in electrical potential energy, whereas this one is lost in e- electrical energy, right? Okay, to other forms such as light. In this case, it's particularly light because it's light bulb. All right. Okay. So with this idea, we actually can move on. Okay. So far we have learned the idea of flow. All right. So flow will actually tell us the current motion, right? Or how charge is actually moving for every section, how much charge is moving across this section in 1 second. Okay, so that's the idea of current. Then we also learn about potential, which is kind of like your gravitational potential energy, right? So if let's say I have a hill, right, uh, something like that, right? Okay, so uh, the energy will be kind of the same over here, okay, because it's on a flat ground, but it will decrease as it goes down, and it will remain the same over here, and it will decrease as it goes down, and it will remain the same over here. So kind of like our potential here along the wire, it will be the same. However, as it goes through a light bulb, it's kind of like this part, it actually goes down, right? Okay, so the potential energy will actually drop, and then it will stay the same as it goes through the wire, and then it will go down again as it goes through another light bulb, and then it will stay the same throughout. All right. Very common misconception is that if the potential is 0 volt, current is not moving. Okay, but it's not true. Okay, even though it's 0 volt, okay, the electrons are still moving because this is a closed circuit. Okay, yeah. So I think we are done. All right, with the idea of potential. Okay, uh, this one I went through the other time. Okay, uh, let's move on to the next part, which is resistance. Now the idea of resistance, right, the definition, okay, is actually the ratio of uh, PD to current in a electrical component. Okay, so I'll unpack this, okay, especially this part on the ratio of PD to current. Okay, so first thing first, the SI unit is ohms, and the formula goes R equals to V over I. Now this is following the definition, but most people, they actually like to memorize it like that, V equals to IR, because there's no fraction. So this is easier to remember lah. Alright, very intelligent rabbit or something. Yeah, very intelligent rasuli. Yeah, okay, or something lah.
Why P
Huh?
P
PD, potential difference. So notice I use the word potential difference and not voltage, huh? Okay, because we are excluding EMF in this, right? Okay, because there's no point in you calculating the resistance of a battery, okay, unless you go to JC lah, right? Then they will introduce you something called internal resistance, but in our syllabus, that doesn't exist. So we will actually treat battery as a zero resistance battery. Okay, anyway, that's not true, okay. So anyway, yeah, so we will treat the battery as a zero resistance battery, and that's why here is a ratio of PD to current. All right. So remember PD, PD is work done. Okay, no need to write this down. I'm just trying to refresh your memory. Okay, PD is actually my work done in driving a charge across the circuit per unit time, right? In converting electrical energy to other forms of energy. Okay, so this is actually my work done to convert electrical energy to other form. Okay, so that's the idea of PD. All right, and then you realize we are actually talking about electrical component. So it is not the battery, but electrical component will include things like maybe your light bulb, your thicker wires, okay, etc. All right, so maybe y'all went through ALP right last time, so there's a buzzer too, etc, etc. All right, so basically the idea of electrical component. Okay, so we just need to unpack this now. Ratio of PD to current, what does it mean, right? Okay, so let me give you a mathematical analogy, then I think it'd be easier for you to understand. Okay, so over here, y'all can write this down if you want. If not, I'm okay, you're not writing down too for this part, because that's a numerical analogy. All right, so given a formula, so R equals to V over I, right? So I have this formula now, R equals to V over I. Now based on this formula, if let's say my resistance is changing, right? So I have two resistance. One is a 10 ohm resistor. Okay, so I have a 10 volt battery. It will need to produce a 1 ampere current, right? So imagine my volt sorry, yeah, okay, so 10 volt here and then 1 ampere here, and then you realize that for 1 ampere for 1 ohm resistor, okay, for 1 ampere current I actually only need 1 volt. Okay, what this means, okay, if we keep current constant, is that for a 10 ohm battery, for a 10 ohm electrical component, okay, let's say a 10 ohm light bulb, okay, it actually needs 10 volt to operate, and for 1 ohm, right, it actually needs 1 volt to operate. Now if you remember what is volt, right, it's kind of like work done. So in other words, what I'm trying to tell you is that for a 10 ohm resistor, I need to do much more work for it to work, for it to actually function, whereas for a 1 ohm light bulb, I actually need much lesser energy for it to function. Okay, and that's the idea behind the entire idea of resistance. Okay, so let me just show you something quickly here. Okay, so over here, I want you all to see the current flow. Okay, so if let's say my battery is fixed, okay, so it's fixed at 4.5 volt, right? Okay, but my resistance is the one changing. All right, so you realize that when so you look at the R, and you can look at the slider here. As I increase my resistance, you realize that the flow becomes lesser and lesser and lesser. Okay, and as I decrease my resistance, the current becomes bigger and bigger and bigger, right? That's because when your resistance is lesser, all right, charges, it actually allows charges to flow more easily. All right, whereas when your resistance is high, it actually restrict the flow of charges. All right, so that's the idea. Okay, however, if we increase the voltage, right, you'll realize my current will increase along with it. Okay, when I decrease the voltage, the current will decrease along with it, because if I keep my resistance constant, so let's get back to the definition. If I keep my resistance constant, right, okay, so let me erase this numerical example for a while. Now if I keep my resistance constant, what it will mean, right, is that, hold on, sorry, I'm muted. All good? Okay, so if I keep my resistance constant, so let's say I have a 10 ohm resistor, right, and let's say for one of the circuit I use a 10 volt battery. Okay, over here I have 1 ampere. However, if over here I use a 20-volt battery, okay, over here I'll have 2 ampere. You realize that my current will increase when my voltage increase for a constant resistance, for a constant resistor, right? So you realize that this is true, and watching the animation, yeah, just a very simple animation, you realize that when I increase my voltage of my battery, my current flow will increase. That is because, okay, when there's higher voltage, okay, you actually get a higher current based on the formula V equals to IR. Okay, physically it will also make sense because since you have more battery, okay, and each charge will only do a certain amount of work, okay, because the resistor only required to do a certain amount of work, okay, what will happen is that you end up having more charges entering that resistor. All right, okay, but take note, if we keep the voltage constant and we change the resistance, this will happen. All right, so basically it's trying to tell you the relationship between IR and V, okay, and actually the formal definition of resistance is if we keep resistance constant, you'll see the relationship between V and I, and they are both linear. That means when V increase, I will increase. When V decrease, I will also decrease. All right, up to this point, any questions? If not, then let me go through the high resistance and low resistance part. Okay, so to actually illustrate how it might look like, okay, I need you to draw out. Okay, so high resistance will look something like that. This is just an illustration, okay, this is not how it looks like in the wire, yeah, or in the electrical component, but a high resistance will look something like that, okay, so that when charges flow in, they actually need to take a very long route, okay, to get past it. So this is kind of like high resistance, okay. This actually restrict current flow. It not only restrict current flow, it actually requires more energy. Okay, and therefore the low resistance one will be the opposite of this, so something like that. Okay, so this actually doesn't restrict current flow as much and would obviously require less energy to go through, right? Because you can go through here. So unless you choose to go from the top, you'll probably end up like this. Okay, but otherwise there's actually quite little resistance in your flow. All right, so that's the idea of low resistance. So if you want to write, so it doesn't restrict current flow as much, and it actually doesn't require as much energy. Okay, so obviously I'm comparing within between these two. I'm comparing between this and this, right? Okay, I'll leave this for 20 seconds. Let you all copy for a while. Meanwhile, if you have questions, can you please raise up in these 20 seconds? Okay, if not, I will just put a pause here for 20 seconds.
So go.
Yep.
In like simple terms, can I just say when V increases, I increases, and when R increases, I increases?
Okay, so maybe I write down for you here. So V increase, I increase. But remember this formula got 3 variable. So that means R must be constant. Right? Then if V
Yeah.
is constant, then when R increase, I will decrease. Yeah? Maybe I should write it in terms of cause and effect. So when R decrease, I will actually increase. Yeah, like that. Okay?
Yes.
Okay. All good. I'll come back here again after I'll meet you. Yeah. I'll just go through what I need to go through first. Alright? I don't want to overload you all with too much info. Okay, we're just left with two questions. I mean two concepts, and then we are done. All right. Shall we move? All good. Okay. Now, so far you have learned a few things. Okay, you have learned the idea of potential difference, EMF, current, and resistance. Okay. Now we're going to lump it all into one circuit. Okay. So I think this is the part where I stop. Okay. So for students at H6, I think you can take out your notes now. Okay. So let's go through this part. Alright, so what it means, right? If resistance is the ratio between PD and current, it also means that my resistance actually change how much current can flow in this circuit. Alright, because you realize, right, the EMF is constant. So if my battery is constant based on the formula, so if V is constant, when my R increases, my I will decrease. Okay, yeah, so basically this is what the formula will allow to happen. Okay, when the resistance increases, it kind of restrict the flow of the current. It kind of cause like a jam. Okay, so when there's high resistance here and here, suddenly the expressway, right, the way that the current flows through, will suddenly have like a traffic jam kind of thing. And when there's traffic jam, obviously the current will decrease. Okay, so compared to having just one light bulb here, if you have two light bulb, obviously the current will be lesser. Okay, but the V is constant. That means the energy given to the charges, right, is still the same because it's still coming out from the same source, right? So if the battery gives you 6 volt every time you touch it, okay, so every time you have a current that comes out from the battery, give the charge 6 volt. Okay, even though the current has changed, okay, the battery is still faithfully doing its job in transferring 6 volt to each charge. Okay, so yeah, just need to take note of that. All right, so let me just run through this example very quickly. So we can see EMF at the battery. So let's say the EMF is 3 volt, right? Okay, and we have two light bulb. Let's say the light bulb, right, is 1.5 ohm each. Okay, so we'll call it RA and RB. Okay, so then we always denote current in a conventional current way. Okay, now, so the current here, right, I need to take note of something first. When will current change? Okay, so in a simple setup like this, okay, obviously we are not going to make any changes to the setup midway. Okay, so let's say we operate the circuit like this. Okay, we call this a series circuit. Why? Okay, yeah, later on I'll explain to you all the idea of series and parallel. Okay, but we can call this a series circuit. Okay, for the main reason because over here you realize that I can actually trace out the current flow in one stroke. Okay, so this is a very quick litmus test on how to see whether a circuit is series or not. Okay, you can start out tracing the conventional current, okay, at the positive side, right? Okay, so you trace out the conventional current at the positive side and try to go towards the negative. If you can do this in one stroke, then this is a parallel circuit. I mean a series circuit. Okay, if it's a parallel circuit, right, you'll never be able to do this. So let's say I have a parallel circuit, right, and I try to do this, you'll realize that I won't be able to trace out a full circuit. Okay, so I can do this. So over here, you realize if I go here, I will not go to the negative anymore, so cannot. And if I do this, over here, if I go up to the negative, then I have this entire chunk that's missing, right, that needs another tracing. Okay, so you realize for a parallel circuit you cannot do that, but for a series circuit you can. Okay, so what's so special about series circuit is that because the current doesn't the current can be traced out in one stroke, right? Okay, in fact the current doesn't split up at all. Okay, so in this case, right, if this is, so using the formula, okay, so let me go through the formula first. So V total equals to I total times R total, right? So if let's say you want to find the current in this circuit, okay, we just need to find IT equals to VT over RT, which is 3 over 1.5 plus 1.5. Okay, so the R total in this case, right, you can just add up the resistance. Okay, so this is 1.5 plus 1.5. Okay, so this is just 1 ampere, right? So the current here will be 1 ampere. the current here will be 1 ampere, the current here will be 1 ampere. Okay, take note that current is constant in this circuit, as it doesn't split. Okay, you all have learned this in sec 2 roughly. Okay, so the idea of splitting is this. If let's say the current comes to a junction, right, then over here I can split into two paths. I can either go here or I can either go here. So this is called splitting, right? However, you don't see this happening here. You realize that everything is singular direction. There's no decision to make whether to turn left or turn right. Okay, it's just all in one direction. So in this case, the current doesn't split, the current will stay constant. Okay, and I need you to know that if we were to increase, so V is constant, right? So if we were to increase R, you realize that I will definitely decrease. Okay, so if the value of the resistance increase, okay, so obviously here I'm also talking about, I better write here, V total, R total, and I total. Okay, so whenever you use the formula, I need you to write the subscript. Is it R total or V total or whatever? Right? Now the next thing we want to find out, right, is how much potential difference this is taking and this is taking. Okay, so knowing that current is the same throughout, okay, so we can just do a simple calculation. VA equals to IA times RA, which is 1 ampere times 1.5 ohm, which will give us 1.5 volt. Okay, so this thing takes up 1.5 volt. Okay, and obviously if this is 1.5 volt, the EMF is 3 volt, then VB is also 1.5 volt. Okay, simple. So this is how you can actually see the concept of resistance, potential difference, and current over in one circuit. Okay, obviously series and parallel, there'll be like a few characteristic differences, okay, which I'll talk about in the next 20 minutes. Okay, then we are actually done with the content for now.
Picture when the current split outwards become half.
Okay, that one we talk about later, can.
Okay.
Yeah, when I talk about parallel circuit, then we talk about current split. For now I want to keep things simple. Yeah, just based on this series circuit, everyone can see, number one, current don't split here. Okay, number two, current is constant, and number three, I want you to be able to see this point, that if my EMF is constant, right, if I add more light bulb, the current will actually start to decrease. Okay, I also need you to be able to calculate VA. I also need to be able to calculate IT. Okay, so same thing, I'll give you all 10 to 20 seconds. Okay, please fill up whatever you need to fill up, and then you can take this time to ask me any question you have. If not, we'll move on to the series circuit already. Yeah.
For the VA, right, it just take 3 volts divided by 2.
You can, but that's if the resistance is the same, then you can do that. Yeah,
If different, then cannot.
if different, then you need to think of the concept of voltage. You want to do that.
Okay.
But usually I will suggest you just use the formula lah. That's the easiest, that's the best way, won't get wrong. Yeah, but if you want to use the ratio method, later we can do one question. I'll show you how. There's another method to do this. Yeah, I'll show you how later when we practice 2 questions together. Okay, any other question? If not, then we go through the characteristic of a series circuit. Okay, so we start simple. We start off with a series circuit first. Okay, now a series circuit is easy to deal with because of its non-complexity of formulas. Yeah, because the current don't split, so everything becomes easy. Alright, let me just scroll this down a bit. Yeah, okay, so in a series circuit, let's say this is 3 volt. Alright, and this is 1.5 ohm also, just like the previous circuit. Okay, so yeah, we just need to fill in this, okay, and then I want you to fill in a few uh, algebraic arbitrary points. Okay, so we call this IA, IB, and IC. Okay, basically they are the current flow. So in a series circuit, right, the characteristic is that I is constant. Hence, IA equals to IB equals to IC. Okay, so this is it for a series circuit. Okay, I also need to know that, so let's say this is RA, right? So we call this light bulb A, and then this is RB, so this is light bulb B. So the PD across A plus the PD across B, right, is equals to the EMF. Okay, which is very obvious. We did it before when we talked about potential difference, right? So the potential here is 3 volt, the potential here is 1.5, the potential will be 0. So the PD across A and B will be equals to the EMF. Okay. And lastly, the R total in a series circuit is given by this formula. RA plus RB. Okay, so if you got C, then you just plus RC and so on and so forth. Okay. Now answering Rasuli's question. Okay, so let me make it simple here. Everyone, okay, y'all done copying this? Can I erase this? Y'all done copying this? Anyone still need to copy? Okay, wait, okay. Can you let me know when you're done? Okay, so yeah, basically this is the characteristic of a series circuit. It's quite straightforward, alright. And if you need, I can even give you all a fourth point, saying that VA, you can calculate it using IA times RA. Obviously, VB equals to IB times RB. Okay, so it's always good to write the subscript. Okay, I need you all to know this is this formula is somehow not being used very often. Okay, V equals to IR, right? Students tend to forget the subscript total. You know, so when they calculate, they may end up doing something like that. 3 total. Okay, so 3 volt is the V total, right? So they write 3 equals to I, which is maybe from our previous calculation is 1, right? Then they times R, but they write it as RA. So this is wrong because this won't give you RA, this will give you R total, right? If you want to find RA, you need to use this. Okay, so make sure you write your subscript properly. Alright, Vashini, you done?
Yes.
Okay, thanks. Okay, so we answer Ra's question a bit, yeah. So let's say I have 2 light bulbs, right, and they are of different resistance. Okay, so let's say I'm going to change the voltage too so that it's more friendly. Let's see. Okay, so let's say this is 5 volt, right, and then over here I have 3 ohm light bulb and a 2 ohm light bulb. Now how would the 5 volt split up? Okay, so based on the formula we can find the current first. So the total resistance is 5, right, so the current is 1. Okay, so this is 1 ampere, so it's 1 ampere throughout. So the voltage of this is given by 3 times 1, which is 3 volt, and then this is 2 volt, right? So if you use the formula V equals to IR, you should be able to get this quite quickly. Okay, because the numbers are quite nice, right? However, is there another way we can do it? Yes, we can. Okay, so just think about the idea of resistance, right? So ask yourself, which one will require more energy to pass through, the 3 ohm or the 2 ohm? Okay, if you have been following up to this point, you'll realize that the 3 ohm will actually take up more resistance, more energy than the 2 ohm light bulb. Alright, so the 3 ohm will actually need more voltage to work. Okay, so the 3 ohm will need more voltage to work. So if I have 5 volt, right, and I have 5 units of resistance, okay, what will happen is that the 5 volt will split up, okay, so that it actually gives more to the one that requires more resistance, more energy, and less to the one that requires less energy, right? So over here, since I have 5 units of resistance, I have only 5 volt of energy, right? So 3 units will come here and 2 units will come here, and then yeah, naturally we will know that this is 3 volt, since 3 units of 5 volt is 3 volts, and 2 units of 5 volt is 2 volts. All right, if I change the value a bit so that this become 10 volt, okay, it still works the same way. So in 10 volt, I split into 5 units, right? So 3 units of 10 volt will be, okay, so if 10 volt is 5 units, okay, so why 5 units? Because I have 5 units of resistance. Okay, this is just a quick check. Okay, I don't recommend you doing this. Okay, actually I recommend you doing these formulas instead. Okay, but in any case, 10 volt I have 5 units, so 3 ohm will take up 3 units, so 3 units will give me 6 volt, and 2 units, you realize it's 4 volt. Okay, you realize that these two will always add up to become this. All right, so yeah, so that's for Rast's question just now. Okay, although I really don't recommend you all doing this, right? I recommend you all following the 4 steps that are written below. Okay, so anyway, this is 1.5 ohm, and this is also 1.5 ohm, and this is what, 3 volt. Yeah, okay, all good with series. If all good, then we'll move on to parallel. Now, for the end of year, right, the question is either a series circuit or parallel circuit. I'm not combining the circuits yet. Okay, so after mid-year, I'll teach you how to combine the circuits together. Okay, so now for a parallel circuit, okay, yeah, same thing, 3 volt, then we call this RA lah. Okay, 1.5 ohm, RB is 1.5 ohm. Okay, to make things slightly more interesting, we make this 2 ohm, make this 2 ohm. Okay, oh, by the way, this is a series in parallel. Maybe I should teach you another circuit. Wait, okay, sorry, can you turn to page 10? Sorry. Yeah, so on page 10, right, I want you all to do this. I want you all to split this into half. Okay, and then yeah, sorry about that. I think there's a printing error. Okay, so for this, for parallel circuit, right, can you write here C page 10? Okay, so write C page 10, and then over at page 10, I need you to make a section on parallel circuit. Okay, so just write a section on parallel circuit only. Yeah, sorry, because that's actually a slightly more complicated circuit. That's a combined circuit, but over here I want to just go through parallel circuit. Okay, so and then I want you to draw a simple parallel circuit. Okay, just with 3 light bulbs. Okay, y'all can do that, right? Okay, so let me just draw 3. Okay, let me make everything look nicer. Okay, so you should have a circuit with 3 light bulb. Okay, okay, so let's start. Okay, so let's say I have a 4 volt battery here and my resistance are all different. Okay, so we call this R1, we'll call it 1 ohm, and then we call this R2, we'll call it 2 ohm, and then R3 we actually give it as 4 ohm. Okay, so we actually have this circuit. Okay, so first thing first, for a parallel circuit, I need to teach you how to calculate the R total. Okay, when I have time, I'll actually teach you how to derive this. Okay, but for now, I need you all to memorize the formula. The formula is just 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and if you have more R, just continue doing the same pattern. Okay, basically they are reciprocal, then inverse the whole thing. Okay, so in this case, it'll be 1 over 1 plus 1 over 2 plus 1 over 4, then inverse the whole thing, which will give you half plus 1 quarter, 3 quarter, so 4 over 3. Okay, so my R total will be 4 over 3 ohm. Okay, so this is how we calculate R total. Okay, so remember this formula quite important. So this is for a parallel circuit. Okay, so for a series circuit, it was quite straightforward. You just need to add up all the resistance together. But for a parallel circuit, it's different. Okay, because over here you have 1 over R1 plus 1 over R2. Basically a reciprocal and inverse. Okay, the sum of the reciprocal, the inverse of the sum of the reciprocal. Alright. Okay, so this is how we find R total. So now to find I total, now just look at this circuit. For this circuit, right, what happened is that the current will actually split up here, and when the current comes here, it will actually split up again. So it actually split up twice. Okay, so let's do some labeling here first. Okay, there'll be a few current to label. So this will be I1. No, in fact, let's call it I0. Yes.
So 1 over 1 plus 1 over 2 plus 1 over 4, then you.
Oh yeah. Wait, sorry. It should be 7 over 3, right? Yeah, 7 over 3, right?
4 over 7.
Huh? You inverse already?
Yeah.
Oh yeah. Sorry. My bad. Yeah, 4 over 7. Okay, so it should be 4 over 7 ohm. Oh, very ugly number. Okay, never mind. Okay, so we call this I0. Then you can call this I1. Then we can call this I2. And then we can call this I3. Okay, and then I want you to call this I4. Okay, so can you label your current like that? Okay, the reason why we label the current like this is because I1 is going through this, I2 is going through here, and I3 is going through here without splitting, right? So over here, only at the junction, okay, there's a recombination. Okay, so now let's define parts of a parallel circuit. So over at this point, okay, this kind of points we call it junction. And for each of the lines the resistors are at, right? So this one we call it the branch. Alright, so you realize that at some junction they split up. Okay, this is a recombined junction. The current actually recombined. Over here at this kind of junction, right? Okay, so maybe at here, this junction is a splitting junction. Okay, a bit messy, but I think it's okay. Okay, so now let's calculate. Okay, so I0 is actually my total current. Okay, so you all need to be able to identify that I0 is actually my I total. The reason, because the current has flown out but it hasn't split up yet, so I0 will be my total current. Okay, at this junction, right, it will split up to I1. Okay, and it will split up to I2, and it will split up to I3. Okay, so slightly before that junction, okay, we actually can recognize I0 as my total. And then you realize I4 is also my total, because at I4 all the current has recombined back already. Okay, so I0 will be equals to I total, which is also equals to I4. Now remember how we find I total. So we have this formula, Vt equals to It times Rt, right? So It in this case will be, okay, Vt over Rt, which is 4 divided by 7, so times 7 over 4, which is 7 ampere. Okay, Okay, so yeah, we have IT equals to 7 ampere. Okay, so this is important. Okay, so you can even add on. So I0 is equals to I total is equal to I4. Now another way to get I total, right, is that if you can add up the current in every branch. So this is equals to I1 plus I2 plus I3. Okay, this is another characteristic of a parallel circuit that you need to memorize or you need to understand. Okay, the rest are just calculation. Okay, but the concept I boxed them in the yellow box. Okay, so this is the idea of I total. Okay, now so the I total is 7 ampere, which is basically I1 plus I2 plus I3. Now remember the very first animation I showed you all, saying that when V is constant, when my R increases, my I decreases. Okay, it kind of applies here. Okay, now first thing first, right, the last thing I need to mention is that what is the potential difference across every branch. Okay, so for a parallel circuit, you need to know that the EMF, no, I wouldn't write EMF, I'll write V total. Okay, so V total is equals to V1 plus V2, sorry, not V1 plus V2, is equals to V1, which is also equals to V2, which is also equals to V3. Okay, so for a parallel circuit, right, this is true. Okay, that the potential difference across every branch is the same. So if the potential difference across every branch is the same, in other words, we are actually able to calculate I1, I2, and I3 now. Okay, because we have R1, R2, R3, right? Okay, so just do a quick calculation. You'll realize something like this. So I1 equals to V1 over R1, which is 4 over 1, which is 4 ampere. I2 is equals to V2 over R2, which is equals to 4 over 2, which is 2 ampere. And finally I3 is equals to V3 over R3, which is 4 over 4, which is 1 ampere. Okay, so a simple calculation of I1, I2, I3 will be something like that, and then you realize if you add the three of them up, you'll get 7 ampere, which is 7 ampere here. Okay, sorry, I went a bit too fast. Some of you are asking how I get 4 over 7 ohm. So you just press your calculator, okay, and then yeah, you should be able to get 4 over 7. If you've forgotten how to do fraction division, so looking at this formula, right? Sorry, those who follow, yeah, I think you're good now. Okay, this is for those who are a bit confused. So Vt over Rt, so V total is 4 volt, R total is 4 over 7. So if you take 4 divided by 4 over 7, you get 4 divided by 4 over 7, which is 4 times 7 over 4. Okay, so this is how you get my 7 over 4. Yeah, so some of you were asking how to get 7 over 4, right? This is how you get the 7 over 4. Okay, it's just mathematical working. Okay, you can just key in your calculator straight if you don't know how to do the mathematical working. Okay, just make sure you key in properly. Okay, the 4 over 7 needs to have a bracket, right? Can they answer you? Well, those who are asking about the 7 over 4. Okay, yeah, so basically that's it. All right, so we have I2, I3, I1, I2, I3. All right, and then you realize that they add up to become I4 because they recombine, and they are also I0 because they came out from that. All right, the V total for a parallel circuit is the same as the V1, V2, V3. It's the same every branch. All Alright, and that's it for a parallel circuit. Okay, anyone has any question regarding a parallel circuit? If not, maybe I put this here up for 20 seconds. Y'all can think of any doubts you might have. For those who are good, can you actually move on to page 12 and then try out question 2? And yeah, you can also turn to page 15 and try question 1 there.
Still go for question 1 in page 11. Can you give the answer?
For question 1 on page 11. Oh yeah, you can try question 1 too. Give you all the answer. Amount of charge Q equals to IT. So I times 0.5 times 120 side 60. Then equals to BQ. V equals to IR. Your current flow. Yep. Okay, can try question 11. I mean question on page 11 and 12. Okay. Then I want you all to make an adjustment. For A and B, right? Okay, I want you to make an adjustment. Okay, so for question on page 13, for part A and part B, I want you all to ignore the 2 ohm. So treat it like as though like it's not there. Okay. So you can try 3A and 3B, just treat the 2 ohm as though it's not there. Okay. So just try 3A and 3B. Yeah, the rest can skip. Okay, so can try page 11, 12 and 13. But for 13, just try 3 and 3B. With this following condition, ignore the 2 ohm. Okay. I'll leave this here in case y'all are a bit confused as to what I'm saying. Okay, so ignore the 2 ohm for 3 and 3B and then only try these two. Okay, the rest no need. Okay, I'll give you all like 5-10 minutes. Meanwhile, if you have any question, you can please ask them. Or if you need to copy anything because I move too fast, please let me know too.